Okay. So fundamentally, I'm going to start with the distribution of a language model. Sorry, so the definition of a language model. And I'm going to define it as a probability distribution over strings. And this is somewhat of an important definition. And it will take some time to get used to or sort of appreciate the mathematical complexity of this, because a lot of people will tell you that a language model might be something that you use for next word prediction. But it turns out that really that's sort of a problematic definition, and that any distribution over strings can be factorized that way, but not every next word predictor is actually a language model. For instance, we'd like our language model to only place probability over strings. An important fact about strings, which is sort of baked into this definition, is that strings are sort of by definition finite. So that means we don't want to place probability distribution over any infinite sequences, which is, if you really want to get into the mathematics of it, something that can actually happen. Okay, so you can think about a distribution. We often write it as P sub theta in this course, as taking any string that's an infinite number of finite sequences. So the sequences themselves are finite, but there's an infinite number of them. Like my dog took me for a walk, I took my dog for a walk, and it assigns a probability value to any string. Why do we write P? P is a very common symbol for probability distributions, and theta is a subscript here that represents the parameters. This is quite common in the literature. Now, theta actually hides quite a bit of complexity. So in modern day language models, we parameterize them by a massive neural network. So in this little, this little bolded Greek letter, we're hiding at times trillions of parameters in the newest models. So to be a bit more concrete with what a string is going to be a sequence of tokens. And the reason I sort of zoom in on this is because I think in a lot of sort of modern papers and modern discussions on language modeling, we sort of leave out what exactly we're modeling. So all Y must be in the model's vocabulary, and a vocabulary is a finite set of symbols, typically. So if you study a bit of formal language theory, you know that an alphabet, another word for vocabulary, is definitionally finite. And these can be characters, words, or whatever. And what we're interested in is a distribution over the Kleene closure of V, that is the set of all strings. However, when we talk about generating a language model autoregressively, that is, we want to go left to right, we have to have a special symbol called end of sequence. An end of sequence is sort of necessary to have this sort of left to right prediction. So it tells us that we're going to be done generating. So this is not the only way. As I said, autoregressive models are common, but they're not the only way. But to be a bit more concrete about what we mean by this is that an autoregressive model is something that you can derive by sort of a slightly generalized version of the chain rule of probability. That is, given some string context here, that is, I have y less than t, and I want to spend some time introducing this notation, because you sort of get to the point where we've both in the papers I write and in the the field, we use a notation that's become standard to us, but might not even be standard outside that. And there certainly aren't many textbooks that treat this yet. So what we do here is that we write strings as bolded letters. So whenever you see a bolded little y here, what that means is that I have a sequence of symbols, a sequence of tokens, and that's a string. So what do I mean by this y less than or equal to t? What I mean is the first t minus one because it's less than t, a string. So this is a prefix of the string. So what I mean by this here, this expression here, is that I'm conditioning on the prefix of y less than or equal to t, and I'm trying to predict the next word. Now, what I said earlier was that we typically don't want to really define a language model like this, because you can get into a lot of nasty cases. But almost all practical cases where you'll see language models will involve locally normalized models, autoregressive models that predicts the next word, that is this yt given a context. And we will often start it with a beginning of sequence symbol to get it off, start off the recursion. So what we can then do is that we can compute the probability of an entire string, for instance, the probability of p bold y, as simply the product of each character in its context. Now, again, you can prove that any language model that looks like this on the left-hand side can be written like this on the right-hand side, by just spending a bit more time with the chain rule of probability. Why is it not exactly the chain rule of probability? I guess in some sense it is. The only tricky bit is that y can be a variable length.